Welcome to the CWI Deep Dive Podcast series. This is one episode in a series of 11, each covering a chapter of Welding Inspection Technology. These podcasts are designed for inspectors preparing to take the American Welding Society's Certified Welding Inspector exam. They are not meant to replace enrolling in a Certified Welding Inspector preparation course or dedicated self-study, but to complement them. Along with our CWI Test Prep app available on the Apple App Store, these podcasts will help strengthen your preparation. You can continue learning at work, during your commute, or wherever you find time. Today's episode is brought to you by AMS Level 3, providing consulting, training, and compliance solutions to help companies build stronger, non-destructive testing programs. Learn more at the link in the video description. All right, today we're launching into a deep dive on Chapter 8, Metric Practice for Welding Inspection. Now, if you're prepping for that CWI exam, getting a handle on metric conversions, well, not just useful, it's absolutely critical for speed and accuracy.
Just a quick interruption to introduce a resource to help you take your training further. The AMS Level 3 CWI Part A Test Prep app is now available on the Apple App Store. Designed for welders and inspectors preparing for the Certified Welding Inspector exam, it offers two modes. Study mode gives instant feedback with detailed explanations, and test mode simulates real exam questions with topic-based results to track your progress. All questions align with the AWS Welding Inspection Technology reference, ensuring accuracy and relevance. Download the CWI Part A Test Prep app today on the Apple App Store and take your study time to the next level.
So our mission today, really solidify SI units, take the mystery out of scientific notation, and get some practice with conversion factors.
This deep dive is an independent educational discussion based on concepts from the American Welding Society's Welding Inspection Technology book. We are not affiliated with the American Welding Society, and this deep dive is not a replacement for purchasing or studying the original text. Our goal is to provide commentary, explanations, and reinforcement to help inspectors prepare for the Certified Welding Inspector exam.
Okay, so let's unpack this a bit. A lot of the welding work here in the U.S. still uses U.S. customary units. So why does a CWI candidate really need to spend significant time mastering SI?
Well, the main reason really boils down to globalization and economics, frankly. The International System of Units, SI, that's the standard pretty much everywhere else. Every major industrial nation.
Right.
So for companies that want to play on the global stage, maybe exporting goods, importing parts, even just working off international drawings using SI isn't just a nice to have. It's an economic necessity.
Makes sense.
And it's not just an international thing either. You've got the U.S. federal government mandating SI for all new scientific and engineering documents.
Yeah, okay.
So you, as the inspector, you're basically working in this hybrid world. You have to be totally comfortable switching between U.S. customary and SI. You need to know both sets of rules.
And I guess to help manage that hybrid environment, AWS developed AWS A1.1, right? The metric practice guide for the welding industry.
Exactly. That guide is all about standardization.
So today, we're kind of reinforcing the standards from that guide, the proper usage.
Precisely. And, the real elegance of SI is its simplicity because it's all based on multiples of 10. It's a decimal system.
Which should make calculations easier.
In theory, yes.
Yeah.
Much easier than fractions and weird conversions. So the common SI base units, the fundamentals. Length is the meter, symbol M, time is the second es.
Okay.
Then you get derived units we use constantly in welding. Pressure or stress, that's the Pascal, PA. Energy is the joule Che.
And since welding deals with such a huge range of sizes, massive bridges down to tiny electronic components, we need prefixes.
Absolutely. Prefixes handle those really big or really small numbers, so you're not writing out tons of zeros, like kilo, which is $103 per kilometer, or milli, $10 for millimeter, very common in welding.
Okay, here's that interesting quirk. The exception in the SI system, and something you definitely need to know for the exam, the base unit for mass.
Right.
It's the kilogram, kg, which seems weird because kilo is a prefix. Why isn't the base unit just the gram? Why did AWS stick with kilogram?
Yeah, it's definitely an inconsistency, and that's why it's important to flag. Historically, yeah, the gram was the base unit, but industrially, a gram is just tiny, impractical.
Okay.
So the kilogram became the accepted global standard for mass in practical applications,
Right.
and AWS basically just enforces that standard. Mass is always denoted in kg in technical docs, keeps things consistent, avoids using the tiny gram unit.
Gotcha. So always kg for mass.
Always kg. And moving to welding-specific units, you'll see. Knowing the right pairs saves time, like tensile strength. That's expressed in megapascals, MPa.
MPa.
And wire feet speed, or maybe travel speed. That's usually millimeters per second around.
Right. Okay. Now, dealing with these really big or small numbers, especially in conversion factors, brings us to scientific notation, which can sometimes look intimidating, but
But it's just a tool, a shorthand, really. We don't need to get bogged down in definitions of root and base. You're technical, folks. It's about using it quickly on the exam.
exactly.
So the key takeaway, you see a positive exponent, like $106. Instantly know the decimal point moves 6 places to the right, the number gets bigger.
Making it greater than 1.
Right. And if you see a negative exponent, like 10.3 at $1, the decimal moves 3 places to the left. The number is less than 1.
Okay. So positive exponent, move right, bigger number. Negative exponent, move left, smaller number.
That's the core of it for quick checks. And the standard way to write it, always move the decimal so it's just to the right of the first non-zero digit.
So like 1,450,000 becomes 1.45 times 10 to the 6th.
Perfect. $1.45 times 166 to 101. And something small, like 0.0078.
Huh. Move it past the 7th. So $7.08 times 10.3.
Got it. $7.08 times 10.3. That consistent format is crucial.
Makes sense.
And the math is easier, too. Multiplying. Multiply the main numbers, the roots, then just add the exponents.
Okay.
Dividing. Divide the roots and subtract the bottom exponent from the top exponent. These are huge time savers during the test.
Definitely need those shortcuts. Okay, before we actually do the conversions, we absolutely have to talk about rounding, because getting the rounding wrong
means getting the answer wrong. Simple as that. And AWS A1.1 has specific rules.
Right, the 2 main rules.
Rule 1, look at the digit immediately to the right of the last digit you're keeping. If that digit is a 5 or larger, you increase the last digit you're keeping by 1.
Okay, 5 or more, round up.
Rule 2, if that digit to the right is less than 5, you just keep the last digit as it is. Don't change it.
Less than 5, leave it alone. Okay, let's try that example. Rounding 837 to the nearest 100.
Okay, the last digit you're keeping is the 9 in the hundreds place. The digit to its right is 3.
Which is less than 5.
Right. So you leave the 9 alone, it becomes 8,900.
Got it. What about 935 to the nearest 10?
Okay, last digit you keep is the 3 in the tens place. Digit to the right is 5.
Which is 5 or larger.
So you increase the 3 to a 4. Result, 8940.
Okay, it seems straightforward, but what's the catch?
The absolute critical point. Rounding must be a single operation, a one-time decision. You look at the digit immediately to the right of your target place value, make the call, and you're done. You never round sequentially, like round the last digit, then use that rounded number to decide how to round the next digit over. Because doing that introduces cumulative errors. Little by little, the number drifts further from the true value. And in inspection, that kind of error drift could lead to wrongly accepting a bad weld or rejecting a good one. It has serious consequences.
Okay, single-step rounding only. Got it. So now we've got notation, we've got rounding. Let's put it together with conversion factors. Table 8.4, basically.
Yep, that table is your best friend for this part of the exam. And using prefixes like mega makes life much easier. Remember tensile strength.
Yeah.
70,000 PSI converts to, what was it, like 482,650,000 pascals.
Yeah, a huge number.
Exactly. Unwieldy. But mega means 106 places left. Boom. 482.65 MPa. Much cleaner.
That's the whole point of the prefixes, then.
Keeps the numbers reasonable. Now, using the actual chart, remember the 4 columns. Property to convert from to P and multiply by.
Right.
Just double check you're looking at the right property pressure, length, mass, whatever, before you grab that multiplication factor.
Okay, let's run through a couple typical exam-style ones.
Yeah.
Example. Convert 40 psi to kilopascals, KTPA.
All right, find pressure in the table. Find PSI in the from column, KPA in the to column. The factor should be 6.895.
Okay, so 40 times 6.895 equals 275.8 kPa.
Perfect. Now let's go the other way. Tensile strength. Convert 625 MPa back to PSI.
Okay, find tensile strength. From MPa to PSI, the factor is 1.450 times 122.
Right. And that 122 tells you?
Move the decimal 2 places right. So 625 times 1.450, move it twice, gives 90,625 PSI.
You got it. 90,625 PSI.
No. Here's the one that apparently trips up a lot of people. Electrode sizes, converting fractions of an inch to millimeters, like a 532-inch electrode.
Ah, yes, the classic trap. What's the vital first step?
You cannot just multiply 532 by 25.4. You have to convert the fraction to a decimal first.
There you go. That's the hurdle. So 5 divided by 32 equals?
So let's see, 0.15625 inches.
Right. Now you take that decimal, 0.15625, and multiply by the linear conversion factor, which is 25.4.
Okay, 0.15625 times 25.4 gives 3.96875, and then we round that.
Yep. Usually to 2 decimal places for millimeters unless specified otherwise. So 3.97 millimeter.
3.97 millimeter. Okay, fraction first, then convert. Got it.
Remember that one. Okay, how about deposition rate? Say 7.3 kilograms per hour,
Yeah.
kgh, to pounds per hour.
Find mass per unit time or deposition rate. Factor from kghh is 2.205.
Correct.
So 7.3 times 2.205 equals 16.0965 pounds. Round that probably to 16 pounds.
Usually to the nearest whole number or 1 decimal, unless the context implies more precision. So yeah, 16 pounds is a good practical answer.
Okay, and finally temperature. The formulas are right there in table 8.4 too.
Yep. Fahrenheit to Celsius.
Yeah.
Take Fahrenheit, subtract 32, then divide the result by 1.8.
F32, 1.8.
And Celsius to Fahrenheit. Take Celsius, multiply by 1.8, then add 32.
C by 1.8 plus 32. Okay. Got to keep those straight. We'd also like to recognize Skaggs Media LLC as the creative force behind today's deep dive. Skaggs Media specializes in helping businesses build a strong presence on social media through strategy, content, and storytelling that connects. Find out more at skaggsmedia.com.
All right, let's wrap up this metric focus by quickly hitting the SI style rules. Getting the math right is only half the battle, right? Presenting it correctly matters too.
Absolutely. Documentation needs to be clear and unambiguous. AWS A1.1 has preferences. For prefixes, they strongly recommend sticking to increments of 1,000.
Meaning millimeter, milli, $10, a meter, base, kilometer, kilo, 103.3.
Exactly. And they actually say to avoid prefixes like hectare, deca, deci, and centi in technical writing. Stick to the thousands.
Good tip. And pronunciation, they call out kilo specifically.
Yeah, it's kilo, not kilo. Just a small point of correctness.
Okay. And remind us about mass versus force again. Crucial distinction. Mass is the amount of matter, measured in kilograms, kg. Force, like weight, is mass times acceleration, measured in newtons, n. Don't mix them up in your notes or calculations.
Right. Now, quick hits on capitalization and punctuation for readability. Unit names.
Lowercase. Always lowercase, like meter, Pascal, joule. The only exceptions are if it starts a sentence or the word Celsius.
But the symbols derived from names.
Those are capitalized. A for ampere, J for joule, N for Newton, PA for Pascal, W for watt.
Okay. And L for liter is often capitalized in the U.S.
Right. Capital L is preferred here to avoid confusion with the number 1. Good point.
Punctuation. Decimal marker is a period.
Yep. Standard periods for the decimal. And critically, no commas in large numbers.
No commas. What do you use?
Spaces. You group digits in threes, separated by a space, both sides of the decimal if needed. Like 1 420 462.1.
Oh, okay. 1 space, 420 space, 462.1. Got it.
Makes it universally readable, avoids the commit-decimal confusion between different countries.
And plurals. If you have 50 newtons.
You write out 50 newtons pluralized. But the symbol, it's just 50N, never 50 N's. The symbol doesn't change.
Symbols never get an S. Got it. Final point. Space between number and symbol.
Always. Always put a space between the numerical value and the unit symbol. It's 4 millimeter, not 4 millimeter jammed together.
For space mm. Okay.
Following these style points just ensures your documentation is professional and universally understood. That's the whole goal of SI standardization.
So wrapping this all up, what's the big takeaway for someone studying for the CWI? Mastering this chapter, Chapter 8, really means taking the guesswork out of a pretty significant chunk of the exam questions.
Absolutely. It might seem like just math, but it's applied math with specific rules.
Yeah.
If you consistently use the AWS rounding rules, understand the shortcuts for scientific notation, and crucially, recognize those conversion traps, like the fraction to decimal one, you can tackle these problems fast and accurately. It builds confidence and saves precious time.
Okay, so time for that final thought, something to chew on.
Right. So we've talked about the global trend towards SI, the U.S. government pushing it. Here's the question. How long do you realistically think it will take before the U.S. welding industry basically stops using U.S. customary units as the primary system on drawings and specs? When does SI become the default, not the alternative?
That's a really good question. Makes this knowledge feel even more relevant, potentially sooner rather than later in day-to-day work. Before we wrap up, a quick reminder that AMS Level 3 is here to support your non-destructive testing needs, whether it's Level 3 consulting, training and mentorship, or compliance solutions like NADCAP and Federal Aviation Administration readiness. To learn more, visit amsl-3.com, and don't forget to follow our YouTube channel for more insights and updates on non-destructive testing.
If you've made it this far in the podcast, I'd like to ask for your support. Please consider buying us a coffee. Your contributions help cover the monthly subscriptions we use to produce these NDT training videos and keep new content coming. We offer 3 levels of support. NDT Level 1, $1 per month. NDT Level 2, $2 per month. and NDT Level 3, $3 per month, or a one-time gift of your choosing. Just scan the QR code on the screen to join and help us continue delivering updated NDT resources right here on YouTube. At AMS Level 3, our mission is to strengthen technicians and companies through consulting, training, and compliance solutions. Subscribe to our channel for more mentoring insights, share this video with your team, and give it a like to help spread the word. Visit us at amsl3.com to learn more about our services and resources designed for NDT professionals at every level. And a special thank you to Skaggs Media, the creative force behind these videos. Learn more at skaggsmedia.com.